Hello everyone, I'm Tianyi, come from the Chinese University of Hong Kong, Shenzhen. Today we will talk about our paper Morphe, a high-fidelity generative model video streaming with a vision foundation model. Let's start with the problem in recent video streaming. In many recent things, bandwidth is unstable. For example, when users are on a train or just self-driving travel in the countryside, the network can drop very quickly. The video streaming has a hard balance. High bitrate gives better quality, but it also increases stalling. Lower bitrate makes the video smoother, but the video quality drops. So the key point problem is how to balance the bitrate, stalling, and video quality. Traditional video codecs are already very strong, but they are approaching performance limit at the low bandwidth. Under low bandwidth, they still need to mailing base to present visual details. So we are trapped in the same trade-off as before. Can we find a new balance among the bandwidth, stalling, and the video quality? To answer these questions, we need to find a more efficient video transmission paradigm. Fortunately, recent video generating model gave us a new opportunity. Models like Sora shows that high-quality videos can be generated from just natural language text. This suggests that a new way to rethink about the streaming. If a model can generate a video from text or compact semantic latent, maybe we don't need to transfer the full pixel video. This led us to a bold idea. Can we transmit the latent representations and reconstruct the video as the receiver? This is the start point of the Morphe. First, let's take a closer look at the video generation models. Diffusion models usually work in a latent space instead of directly generating pixels. After it finishes denoising in the latent space, video decoder maps it back to the pixel-level video. This decoder is part of the vision foundation model. It also has an encoder, which maps the pixel videos into continuous latent space, and the encoder is used to when training the latent space diffusion model. For video streaming, this gave us an important opportunity because the vision foundation model has strong zero-shot ability. It can encode and reconstruct many videos without training a new model for each one. However, continuous latent space are still too large for practical video streaming, so we need one more step to make them smaller. Recent works design a type of video foundation model with a quantizer. The key idea is to add a codebook. Instead of using high-dimensional continuous latent, the codebook maps them into the discrete token indices. This greatly reduces the amount of data. In this setting, it can achieve more than 300 times compression while keep strong zero-shotting ability. Now the opportunity becomes clear. We can transmit discrete semantic token and let the receiver reconstruct the video. This sounds promising, but existing methods forced to replace the video streaming due to the critical limitations. First, the neural codecs can train a content-specific model for each video segment, but this brings extra model transmission, high overhead, and long latency. For the generative models, it can use package representations, but they often don't match the original video well, and they are highly sensitive to packet loss. So Morphe needs to keep the generative compression while solving three practical problems: fidelity, latency, and loss resilience. The first challenge is fidelity. Video foundation models preserve semantics such as scene objects and main structure, but they often lose high-frequency details such as texture, edges, and maybe text and sound patterns. So as shown in the example, the decoding frames may look good, but it is not just true enough to the original frame. This motivates our first goal. Can we design a fidelity-aware generative codec that keeps the high compression while restoring the more visual details? The second challenge is latency. If we directly apply a video foundation model to high-resolution video, the computation is too heavy. Existing video foundation models only run at around 1 to 6 frame rate on the 1080p videos. This is far below the real-time streaming, so even if compression is good, the system can't be used if encoding and decoding are too slow. This motivates our second goal: can we shift heavy model inference to low resolution and then recover original size video with a super resolution model? The third challenge is packet loss. Generative-based streaming are very sensitive to token loss. If a few tokens are missing, the decoder may generate critical artifacts. This is difficult and this is very different from the normal pixel codecs because each semantic tokens can affect a large vision region. So the third goal is to make a generative-based streaming network adaptive and loss resilience, enable video quality degrees smoothly under lossy network. Based on these three challenges, we built Morphe. Morphe is the first vision foundation model-powered video streaming system. It aims to preserve smooth experience with high compression while maintaining high quality, low latency, and strong loss resilience. And in other words, Morphe is designed to improve the imbalance we introduced at the beginning: bandwidth, stalling, and video quality. Morphe has three main modules, and each module maps to one challenge. First, the visual enhanced generative codec provides a high-fidelity video reconstruction. It is designed to recover details that are lost by high compression. Second, the resolution adaptive scaling accelerator reduces the model computation and enables low latency video transmission. It reduces the cost of the model inference on high-resolution video. Third, the network adaptive streaming controller provides a strong packet loss resilience. It just adaptive transmission based on the bandwidth and handle pocket loss as the receiver. Next, I will explain these three designs in order. The first part is the visual enhanced generative codec. One issue in generative reconstruction is temporal consistency. Morphe processes video in groups of pictures like traditional codecs. As the boundary between two groups, the last frame of the one group and the first frame of the next group may don't match perfectly. This mismatch can cause frame jitter. Morphe optimizes the bandwidth frames of each group and then balance them. This can smooth the video without sending extra data. The next design is a similarity-based token selection. With the bandwidth is limited, Morphe can't send all tokens, but dropping tokens randomly is not a good idea because the different tokens may have different importance. So Morphe compares corresponding tokens in IMAP and PMAP using constraint similarity. If a token changes a lot, it may contain important information. So Morphe keeps it first. And if a token changes very little, it seems useless, so we can just drop it. This gives Morphe scalable video coding under ultra-low bit rates. Because of high compression, semantic tokens may miss small pixel-level details, such as pattern and text. So to handle this, Morphe as a pixel residue design. It first decodes the frame from the semantic token and then computes the residue between the original frame and the proxy frame. Most residue values are small or just close to zero. So Morphe averages residues within each temporal window and compresses them with entropy encoding. This brings a very high compression of residue data. In this way, Morphe uses tokens for the main semantic structure and the residues for fine visual details. Now let's move to the second module, the resolution scaling accelerator. The main idea is easy. Morphe downscales the input video before model encoding and decoding. This greatly reduces the computation and the bit rate. After decoding, Morphe uses a super resolution network to upscale the video back to the original size. So the heavy foundation model encodes smaller video, but the final output is still high resolution ones. This is a key reason Morphe can support real-time high-fidelity video streaming. The third module is the network adaptive streaming controller. This controller estimates bandwidth with BBR. With the bandwidth is very low, Morphe uses 3 times downsample mode, drops unimportant tokens, and turn off residues. When bandwidth is better, it sends 4 tokens and some residues. When the bandwidth is high enough, it switches to 2 times downsample mode for better quality. This is how Morphe maintains the online balance between the bandwidth quality and the smooth playback. Packet loss is another important part of the controller. Morphe converts packet loss into incomplete token generation. The key idea is to treat the lost packets and self-dropped tokens in the same way. And the decoder reconstructs the video from partial semantic tokens. Because the decoder has a generative repair ability, it can just fill in missing region without waiting for retransmission. This design enables low latency streaming and strong packet loss resilience. This slide shows the training flow of the Morphe. In the stage 1, Morphe trains the super resolution model with the pixel loss and the flow loss. The pixel loss improves the visual quality, and the flow loss helps to reduce the jitter across different frames. In stage 2, Morphe keeps the super resolution model frozen, while flatten the large vision foundation model, and we just add gain loss to improve the visual quality. The whole training flow uses ultra-long video dataset with 16 NVIDIA A100 GPUs. And the full training takes about 185 GPU hours. Morphe is also implemented as a real streaming prototype. The prototype uses 2 NVIDIA JSON or Ring devices. One device is a sender and the other is a receiver. They are connected by a network cable for end-to-end transmission. The streaming system is built on WebRTC framework. So Morphe is not only an offline codec evaluation, it is also a real-time end-to-end transmission system to over lossy networks. Now let's look at about the evaluation. First is visual performance. Just on 1080p videos, Morphe achieves comparable visual quality to H.216.5 codec. We are using about 62% less bandwidth. This means Morphe has more than 2 times higher bandwidth efficiency. At only 400 kilobits per second, Morphe still reaches about 18.5 VMAF. This shows that Morphe improves the bitrate quantity balance under the ultra-low bandwidth. And we just also test Morphe on 4 datasets. Across this dataset, Morphe consistently achieves the best VMAF. Compared with the neural baseline, the VMAF can be up to 2.5 times higher, and it keeps strong same leaps and this performance. This means that the improvement is stable across different video content. Next, we evaluate loss resilience. Temporal consistency is important because the jitter is easy to notice. With temporal smoothing, Morphe achieves about 10 dB higher PSNR than neural codecs. On the latent side, even with 25% token loss, more than 19% of the frame are still below 115 milliseconds. So Morphe not only improves the visual quality, it can also keep the video stable under the lossy network. This slide shows the evaluation of the frame rate under packet loss. At the 25% packet loss, traditional codecs lost many frames. In some cases, the video becomes nearly unwatchable. Morphe still maintains high frame rate under the maybe the same pocket loss. It achieves up to 14.4 times improvement over H.216.6. This shows that Morphe can keep playback smooth and when the network is very unstable. Here we look at the visual quality under pocket loss. From 5% to 25% packet loss, Morphe maintains stable VMAF leaps and this performance. At 400 kilobits per second, it achieves up to 4 times VMAF improvement over baseline codecs. This is important because it shows Morphe can improve both smoothness and fidelity in lossy networks. Finally, we evaluate real-time performance. Morphe can run across different platforms, from cloud service to consumer device and even edge devices. With adaptive resolution scaling, the encoder and decoder can both reach real-time performance, especially in 3 times downsample mode. This shows that Morphe is not limited to large code survey. It can also work on the even edge device, which is important for practical streaming development. Here is a short demo of our Morphe. We compare Morphe with H.2 16.5 using a 1080p videos. So to conclude, Morphe is the first end-to-end vision foundation model powered by generative video streaming system. It addresses the K-balance problem in video streaming, boundwise stalling, and video quality. Of course, Morphe still have some limitations. It can struggle with very fine details and text-heavy content because vision foundation models based reconstruction will lose some details. The takeaway is simple. We think we don't need to transmit every pixel of the world. We only need to transmit the semantic keys that allow the generative model to reconstruct it. This is all of my talk. Thank you for your attention.